Right. Hello, everyone. This is our presentation for our AI practicum. My name is Ethan. My group mates are Michael and Carnell. And today we were going to be talking about our project, which is using reinforcement learning to make a poker bot. So a very brief overview about poker, specifically one of the most popular variants, which is No Limit Texas Hold'em. Poker overall is a game that is, contrary to what people believe about gambling, is actually very mathematical and employs a lot of game theory principles. In summary, what happens is that each player receives two private hole cards. There's a round of betting followed by cards being dealt on the board for everybody you use in rounds of 3 cards followed by 1 card followed by 1 card. There are 2 ways to win this game. The first is to make the best 5-card combo out of all the cards available on the board as well as your own 2 cards. The second way to win is through betting, in which case after you bet, everybody else folds and automatically forfeits the pot and you're rewarded the pot. So poker is a zero-sum game, which means that the amount that is lost by all the losers is equal to the amount that is won by all the winners. It's also a game of imperfect information. So contrary to a game like chess, where you can see the whole board and all your opponent's pieces, poker is a game where you only know about your own hole cards, but you have absolutely zero information about the opponent's hole cards. And the reason why, as for the machine learning aspect, we decided that reinforcement learning is the best way to approach this, because contrary to other problems such as supervised learning, poker is a game which does not necessarily have fixed outcomes just because of the unlimited different ways of playing the game. So there's no fixed outcome for various scenarios. As a result, creating a reinforcement learning agent which would learn on its own what decisions to make through rewards and punishments. In this case, those would be the payouts of how much we win or lose per hand. We felt that reinforcement learning overall will be very appropriate to tackle a problem like poker. Delving really quickly into what kind of 5-card combinations you can have to win. As you can see, there are quite a lot of complex combinations. So for example, you have a straight, which is 5 consecutive rankings in a row, in this case 6, 7, 8, 9, 10. You also have combinations such as a flush, which does not care about what the rankings of the cards are, but rather the fact that they're all the same suit. You also have combinations such as 3 of a kind plus 2 of a kind combined into 1, and you have combinations of straights and flushes. The reason why I really briefly bring this up for your knowledge is also because later Michael's going to talk briefly about how we try to optimize evaluating the strengths of our hands through based off all possible combinations.
Yeah, so in terms of prior work done in developing poker AIs, here are some of the prominent ones, but at the heart of all of these algorithms is the use of counterfactual regret minimization, also known as CFR, which is also the center of our projects. Next slide.
Right, so going off of what Carnell said, there's 2 things I briefly want to talk about. The first one is regret matching, and the second one is Monte Carlo counterfactual regret minimization. So what exactly is regret matching? So regret matching is an algorithm that seeks to minimize regret about its decisions at each step or move of the game, or in this case, when the hand is being played. As the name suggests, it tries to learn from past behaviors to inform future decisions by favoring the actions it regretted not having taken at each stage. So in this model, there are positive and negative values for regret. Negative regret implies that we do not regret not taking this action, and positive regret implies that we do regret having not taken this action. This can most easily be visualized using a game tree. If I direct your attention to the picture, we have a tree-like structure where yellow nodes represent our actions, blue nodes represent our opponent's actions, and red nodes represent terminal nodes, which is where the hand ends. So, for example, in this picture, at the root, we are just dealt our 2 starting hands. In this case, it's Queen Jack. We can choose either to check or to bet, for example, and then based off each branch is a sequence of each branch represents a sequence of actions taken by both ourselves as well as our opponents. And lastly, at the terminating nodes, we will be returned our expected payout. So it's like how much we won or lost at each hand. And this way we can perhaps you can now perhaps see intuitively how we can track our regret, which is like perhaps how much more we would have won if we had taken this route instead of the route that we did take. So going on into Monte Carlo CFR. So as mentioned earlier, CFR with its like traversal of some kind of game tree. The problem with general CFR is that poker is such a massive game. There's too many states. There's to my understanding, there's over like 10 to the power 30 possibilities. If we try to implement regular CFR, this would just simply be way too time consuming. There's too many possible iterations to consider, too many possible player actions, as well as too many chance outcomes, like too many possible outcomes of what like cards could come out. So in order to resolve this, we use the idea of abstractions and what's called chance sampling. Essentially, the idea is we try to group different scenarios together based on how similarly they would play out and how within each group, such small differences are likely to not influence the outcome of the hand that much, and thereby not really factor very, very little into the algorithm's computation. A quick breakdown of two such abstractions are card abstractions and bet abstractions. So the more simpler bet abstractions is essentially the idea. For example, if the pot is $20 and I bet $5, which is a quarter of the pot, well, it would not make much difference if I bet $4 or $6. These are all very similar values in terms of proportion of the pot. So thereby, I can group these really similar bet sizes together instead of having to consider them individually. But I would still break them if they are really noticeably different. For example, if I bet $5 versus $20, which is 100% of the pot versus 25% of the pot, then in that case, you could argue that there would be a noticeable influence or noticeable difference in how our opponent would react, and thereby those would actually justify two different branches on the tree. Likewise, for card abstractions, let's say my hand is ace-4 and the flop comes ace-10 jack, in which case I have a pair of aces and my last two cards are 10 jack and 4. Well, if I were to have ace-3 or ace-5, for example, this would not necessarily impact the strength of my hand. I'd still have a pair of aces with a 10 and a jack and a very low card, like a 3 or 4 or 5. So by that logic, I could group these hands together as well, simplifying with the overall classification of cards, and I wouldn't have to make as many iterations or as many different kinds of traversals. However, this is still really effective because it would still be able to differentiate between hands of different, very like polarizing strengths. So for example, comparing the example, I had a top pair with a hand that I'm holding like ace-10, in which case I would have a 2 pair aces and 10s with a jack. Obviously, this would play out very differently because I have a much stronger hand now with ace-10, and as such, there would be a separate branch for this potential outcome.
Well, now we talk about the implementation details of our algorithm. For our cards in our algorithm, we use a prime number algorithm in order to facilitate our evaluation. There are 13 unique ranks in a deck of cards, and we mapped all the unique ranks to different prime numbers starting from 2 to 41. By using this mapping, this is based on a property of prime numbers, in which if we take the product of any 5 prime numbers together, the product of the number will guarantee to be corresponding to a unique combination of 5 different ranks. We can use this to our advantage by creating a lookup table for all the different possible product of the 5 prime numbers multiplied together and have them map to the strength of their hands respectively. This is a very efficient way of evaluating how strong a hand is for any hands besides a flush and a straight flush. And those two are the only exceptions because the strength of those hands depend on the suite of the cards rather than the rank. For those type of hands, we instead use a unique binary number 1, 2, 4, 8 and assign each of them to a suite of the card so we can check for whether all 5 cards are the same suite by using basic simple binary operations. We'll also have a separate lookup table for suited hands as compared to non-suited hands, in which we can use suited hands for cards that are all the same suite in order to get the strength of the ranking, to get the strength of the hand, and for non-flush hand, use the other table. Once we plug the hands into the table, we'll get an integer value in return that corresponds to the strength of the hand, in which the lower the number is, that means the stronger the hand is. Let's say we have 2 different 5 sets of cards, and we plug both of them into one of the lookup tables. Then And when the lookup tables return two different integers for each of the strength of the hands, the hand with the lower integer that has been returned to a lookup table will have the stronger hand. This is a very efficient way of calculating which hand wins in Showdown for each of our hands that will be useful when we're training the module. For a strategy implementation, we chose to have a strategy for a player that is stored in the form of a 3D array. In order to index through an array to find an appropriate strategy for each different scenario, the strategy is determined by which round the hand is in, whether it's pre-flop, flop, turn, or river, or how strong the player's hand is, which is kind of like what Ethan talked about previously, in which we will determine how strong a hand is, such as a pair versus two pair versus trips. And for each of these different hand strength, we will group them together as a specific scenario in which we'll group them as the same scenario and have the same strategy play a different way because how strong the hand is similar. By this grouping, it speeds up our training process by a lot because we have to worry about a lot less different scenarios. In addition to having this being in addition to having more data points on each different scenarios that we can fine-tune our distribution even more. Once we can index through a 3D array, we will retrieve finally an array which consists of a distribution of probabilities corresponding to actions that the player take and the likelihood of each action being taken in that specific scenario. And the point of our entire CFR algorithm is that we'll call this strategy and then find the appropriate action for a player in this specific scenario. And afterwards, we'll recalculate all different scenarios to see which one has a best regret. And then we'll fine tune and adjust the distribution of the strategy in order to make a new probability distribution that will favor the action that generate the most positive regret from.
All right, diving into our implementation details of the Monte Carlo CFR algorithm. So essentially, the high-level view of our algorithm is we trained our CFR algorithm by running CFR for each player over T iterations, given a vector containing both players' cards, their action history, and their reach probabilities, which correspond to their probabilities of reaching a certain game state node. And essentially, if the history H is terminal or it's a terminal node, which in our case is either when the agent has folded or when the round is over and a player has won, then we return a utility value. If this is the beginning of the game and this is a chance node, then the algorithm samples a single outcome due to chance sampling and recursively calls CFR again. If the node is neither a terminal node nor a chance node, then the algorithm for each possible action recursively calls CFR again with the new history and an updated reach probability. And after that, we then update the vectors corresponding to our regrets and strategies.
So unfortunately, our model, our agent did not perform as well as we expected. Michael will go into that a bit more later, but basically we wanted to give a quick overview of what our evaluation would have been if it worked out well. Essentially, we would have had our AI play against three different kinds of opponents. The first kind is human players, which is us. We have experience playing poker, and we'd be very interested to see how the AI would perform against our strategies. The next two opponents would be different kinds of dummy bots. The first dummy bot would just make purely randomized selections regardless of the AI's choices, thereby creating somewhat of a non-exploitable but at the same time extremely non-optimal strategy. The second is the exact opposite, which would be very fixed decision making. This might be somewhat more optimal, but at the same time extremely exploitable.
Here's an example of the result of when we were trying to train our data. As you can see here, these numbers, the numbers that follow pre-flop, flop, and turn correspond to action taken by the player, in which 1 corresponds to the player calling the bet that they're faced by, and 8 meaning they re-raise to 3/4 of the pot size, of the current pot size. As you can see after each block of actions by the player, we can see a row of regrets in which each action's regret are calculated after the tree is traversed through and recursively calculated, in which there are both negative and positive regrets. And positive regret means that the action taken generated the best positive outcome and that it should be taken out even more further down the line when fine-tuning our distribution. As you can see here, the action 8, which means re-raising, has the best possible regret, meaning that further down the line when we will adjust the CFR will adjust the distribution of this specific scenario to favor taking action A more than before. Here's another example of our evaluation, which we can actually see what went wrong in our algorithm. As you can see here, instead of training and converging towards a more optimal policy, our algorithm for some reason started to converge towards a policy in which it'll keep re-raising by 2/3 pot over and over and over again, though against the opponent, while the opponent is also doing the same thing. And in the end result, both of the players are stuck in a loop of this very non-optimal policy, which kind of ruined the strategy that we were hoping the bot would come up with.
So overall, going off Michael said, in short, we were unsuccessful in implementing RL bot that could play poker. In hindsight, we were probably too ambitious. We did spend a lot of time trying to hard code the poker game engine and environment, as well as the algorithms, and we also spent a lot of time trying to design optimizations. But ultimately, somewhere along the line, our implementation went wrong. We also thought of the fact that we were too ambitious in terms of deciding to implement a bot specifically for this variant of poker. When we were doing our research, we found a lot of papers implementing different kinds of CFR, but we come to realize why they had these implementations for much more simplified games of poker, which had much smaller state spaces. And as such, you could imagine how when it came to designing the algorithm and building the game tree, there's like these game trees have much shorter depth. As a result, and like much fewer iterations were required to converge to the optimal policy. They also just overall perform faster and require less CPU. In terms of further improvements to what we did try to do, we thought we could next time try to refine our CFR algorithm even further. We could try to more precisely partition hands into different categories, thereby not only would we improve our computation time, but we also improve the overall outcome in terms of performance of our agents. And lastly, we will have also like to evaluate our algorithm against some form of exploitability, which is defined as like the overall weakness and vulnerability of our agent's calculated strategy profile. And we would like to measure this exploitability over the number of nodes visited by our algorithm. Intuitively, if we traverse more nodes in our algorithm, we would thereby have more training data. We would expect our agent to perform more optimally, and therefore we would expect an overall downward trend in this exploitability. Unfortunately, we were unable to achieve these things, in hindsight, we would like to try to take these considerations into the future if we have the opportunity to work on a project like this again. And on that note, thank you for listening to our presentation.